and more elaborate. So for starters, you should get to this page, and down at the bottom here, there's this 3GC3 simulations buffet link, right? Now, if you click on that, there's this wonderful set of simulations that Ian Hayward has prepared for us. And the great thing about this resource is that it's available online, so you can actually pretty much take it home and play with it yourself. You know, play with it tonight. Go back to it when you come home if there's something you'd like to try out again. And the way it's structured, he's done. There's about 6 or 7 different simulations, and we'll be kind of going through them as the week goes along. So for today, we'll probably concentrate on the first one. If you click on that, you get something we call a perlog, which is basically a mix of text, which describes what's going on, and data files. So the data files you're going to need for running the actual exercise. They're all included in this log. So basically the first simulation we're going to do, probably the first and last today, is just a simple simulation of the Cat7 telescope. And so for that we need a measurement set. You can get it through this link, and the sky mode. Now the only tricky thing is that you're going to need those files on Drake or Elwood, you know, on the machines where you're actually running the simulation. Whereas if you click on the link here, you're going to download the files locally, which is not what you want. So what I suggest you do so if you log into your assigned machine, and I suggest you create a subdirectory for this exercise, just to keep things neat. But you can also just do it in your home directory. I'll do it in a subdirectory. So I'll call it EX1 for exercise 1. Now that you're in this directory, what you want to do is you want to download the files for the simulation. And the best way to do that is if you right-click on the link here, and you say copy link address, so that puts it in the clipboard, and then you go back to the terminal and you say wget. That's the command for downloading files off the internet. You say wget and you paste the link, and that gets you a copy of the file into your directory.
Just doing it again on the.
So you go here, you right-click on the link, and then depending on your browser, this menu is going to look different. But in general, there's something like copy address to clipboard or copy link address or something like this. And so you've copied it to the clipboard. Now you say wget, and you paste from the clipboard, and there you've got the files in your directory. The other thing you can do, if that doesn't work for you, now that I have them in my directory, you can copy them from my directory instead of copying them from the web. So in principle, you could just take the easy way out and copy everything from this directory into your own, right? Now the next thing you need to do is the measurement set. As you can see, it's a tar.gz format, so you want to unpack that. And the command for doing that is this one. Or again, if you copy the directory from me now, you'll get done pack measurement set. But this is something you should make a note of this, because when you use this resource for your own exercises, this is something you're going to have to do anyway. You're going to have to download the tarball and unpack the tarball. So once you've done that, you should have two files in your directory. You should have a measurement set, which is similar to the measurement set we were working on with Cyril. And you should have a sky model file ending with .lsm.html, right? So once you've got those files, we can go back to our browser and see what Ian has told us about this whole exercise. Actually, if you come back to this yourself, you'll see he's got enough comments in the text here to tell you how to do it, right? You'll have to tar zxvf the file ms for it to become useful and so on. So he's actually tried to structure this whole thing as a self-contained tutorial, which you should be able to repeat on your own. Okay, so now that we've got those two files, the first thing you can try is looking at the sky model. And you can do that with a tool called Tigger. And you give it the file name. So you should get something like this on your screen. So what you're seeing here is essentially, well, it's a plot. A sky model is a list of sources. Nothing more elaborate than that, really. It's just a list of sources. So over at the top here, you see a list of sources with their coordinates. This is their distance from center, and this is their brightness, I. So you can see this is the brightest source over here, 1.88 Jansky. Then this is the next brightest. And when you scroll your cursor over the sources, it highlights on the plot where that source actually is on the sky. So what this is what we call a sky model, right? And what we're going to do is we're going to try to simulate an observation consisting of these sources on the sky. So the way to do that, let's see what Ian tells us to do next. Well, he tells us to read a lot of text. And this will be, you'll probably want to go back to this and read it. It's, I'm going to show you what to do, right? But he's got detailed explanations in here. Basically, you have to run a piece of software called MechTrees. And the way you run it is you run a command called mechbrowser, MEQ browser. And once again, I remind you that there is this very handy feature called tab completion. So if you type just the first 4 letters and then press tab, it completes the command for you. It will save you a lot of typing. Once you run the browser, you should see something like this on the screen. Now there's two, when you use MechTrees, there's actually always two programs running. There's something called the mechbrowser, which is the graphical interface, and there's something behind it called the mechserver, which does all the actual computations. So whenever you start the browser, the first thing you need to do is also start the server. And you do it through this dialog here. Basically, you push start, and then this is what you should see. Okay, and the next thing we should do, following Ian's instructions, the way MechTrees works is you load scripts. You load Python-like scripts which determine the structure of your simulation. So we have to get a script somewhere, and I think he tells us to get the standard simulation script from MechTrees, and I'll show you where to get it. So you need to do this. So what you want to do is you want to get to a point where you've got this Python script in your directory, where you have the measurement set in your directory, and where you have the sky model, right?
Do you need to edit that script, or is it just for running?
No, you don't need to edit that script. The script is standard. It's just a standard system-wide script that we always have. Okay, so once you've got that script in place, we can go back to the browser here, and we can load the script into the browser. And you do that through the TDL menu here. You go to TDL, load TDL script. This gives you a little dialog. This is a script. the copy command. This one here. Okay, has anyone not got the script yet? Yeah.
I'm trying to get that CP. Oh. And then not, okay, then this is my trees.
And now you go to, okay, so if you've got the script, anyone else? Everyone has a script? Great. So, whoa. Okay, so if you've got the script, you go back to the browser,
Okay, that part I don't have yet.
and then you go to TGL, up there,
Yeah.
and load TGL script. Or if you're lazy, you just press Ctrl-T.
And that turbo sim, right?
Yeah, and now you load this TurboSim thing, and with any luck, you're going to have a dialog like this come up. Now, what TurboSim is, it's basically it's like an all singing, all dancing simulator script, which can simulate just about anything. So, and there's about 1 million options in this menu, which determine what you're going to simulate. Now, what we want to set is something very simple for starters, and then later on your own, you can play with these things to, to make more elaborate simulations. And if you go back to your web browser, Ian actually explains quite a lot about what you want to set up, and he even provides screenshots for you. So there is a screenshot here in the Simulations 101 chapter. If you click on this thing here, it's showing you exactly what options to set up. But basically, I can guide you through the basic ones. The first one is the measurement set, and that's the measurement set which you've hopefully unpacked, right? Now, the next option you want to specify is the sky model. So you want to open up the sky model menu here, and you want to say use Tigger sky model, and then you have to specify the name of the sky model. And I think this is pretty much everything you have to set for now, right? We'll do a very simple simulation where we're just taking a measurement set and putting the sky into it. So that's the only two things you have to specify. And once you've done that, you go press compile down at the bottom here. And with any luck, you'll get to the next dialog. So what's happened now, the script has compiled what we call a tree, which will do the simulation for us. We're not running the simulation yet, right? We've just prepared the mechanism. And the next screen, this is where we start the simulation. So here we have to tell it which column of the measurement set to put the simulation into. So we might as well put it into corrected data. And yeah, that's pretty much it. You don't have to specify anything else. This mysterious option tile size, that just determines what chunk of data the thing processes at once. It always goes through all the data, but it breaks it up in chunks, so that you don't use too much memory. You can leave it at 8, you can make it bigger, it really doesn't matter for the simulation. Basically now if you press simulate, it's very exciting. You should see a little progress bar at the bottom here, and you'll get a message flying by that your simulation has completed. Now, how do we see that our simulation has completed? We can actually, before we run it, what we can do is we can open a bookmark. So if you go to the bookmark menu here, And the bookmark menu provides you with standard kind of predefined visualizations of the data that's being produced. So a useful one is something called the output inspector plot. So if you go to bookmarks and select the output inspector plot, you'll see another little window. There's nothing in this window right now because bookmarks only show stuff when you're actually running the simulation. So to see something in there, what we need to do is we need to run the simulation again. And to do that, you click on that button there, the exec button. Again, this is all explained in Ian's text, so you'll be able to find it. So if you go back to TTL exec, and now press simulate, what you get here now is it's a summary plot of all the visibilities that have been written to your measurement set, right? Now, these labels here are baselines, so these are baselines between antenna 01, 02, 03, 04, and so on. And this little squiggly line is showing you, I think by default it's showing the visibility amplitude, right? And because we've simulated a field that contains a whole bunch of sources, you're going to see, a whole lot of things going on here. If you want to look at phases instead, you can right-click on this plot, and you can say plot complex values as phase. That gives you the phases that you've been spitting out into the measurement set. And well, you can also look at it as real and imaginary. Oops. Let's put something up there. You can look at the four polarizations, which in this case is not very interesting because our sources are intrinsically unpolarized. All sorts of things. There's another set of bookmarks you can look at. So the inspector gives you a summary of pretty much all the baselines in your measurement set. If you're interested in a particular baseline, you can get it through this little menu of bookmarks. So for example, this one here will show you baseline 01, 03, 02. But again, you have to rerun the simulation to get anything into those displays. So I'll run the simulation again. Now basically you're seeing the visibilities per baseline. In this mode of display, it's the real and the imaginary part. So this sort of thing is kind of, well, basically it's useful to check that data that's going into the simulation is actually sensible. Now, of course, now that you've made this, now that you've run the simulation, essentially what we've done is the equivalent of writing the data to the measurement set with PyRap, as in the previous exercise. So now we can image it. In principle, you could image it with the same LW imager command that you had in the previous exercise, but there's an easier way to do it through the menu here. So if you open up the TTL exec menu again and open up imaging options, this is basically just an interface to the LW imager command. So it tells it which column you want to image, what to do with frequency channels, and the most important thing to set here is the size of the image. So let's say we want an image that's 1024 pixels across and 180 arc minutes. And I think that's probably all we need to specify. So if you set these two options, 124 and 180, then you can go ahead and make an image. And there you have it. So that's basically our first simulation. Because this is Cat7, it's an interferometer with only 7 antennas in it, we have much poorer UV coverage than in the case of LOFAR, in Cyril's exercise. So the point spread function of the point sources is a lot more, a lot poorer. So all these rings, what you're seeing is the point spread function of the sources. Now, one nice thing you can do, as you noticed, Tigger, this is the same tool we used to look at the sky model in the first place, right? So now it's showing us a FITS image. we can look at both of them together. So if in Tigger you go to the File, Open Model menu, you can actually load the sky model together with the fits image. And I'm kind of running out of screen real estate here, but if you make yourself a bigger window, now you're basically seeing crosses for the positions of the sources in the model superimposed on the image we have produced. So has everyone got to that state? Okay, what we can do is I propose we add a little wrinkle to this simulation. That's going to show. Rick, I don't think you mentioned noise and sensitivity.
That's in the lecture I'm writing right now.
Okay.
Tomorrow morning.
Right. Well, anticipating Rick's next lecture a little bit, what we're going to do is we're going to run the same simulation, but this time, if you go back to TTL options, to the simulations options, this time we're going to add some noise to the simulation, right? And noise, of course, is inescapable in any measurement, as you know. So the visibilities that we get off the correlator, they're actually subject to essentially to additive Gaussian noise, right? And Rick will tell you all the details tomorrow, and he'll give you a formula. You can kind of work out what the noise level is going to be based on your aperture size, based on the temperature of your receiver, etc., etc. So there's a formula you can use to plug everything in. Here the simulation cheats a little bit.
Sorry, how do you fix that screen?
TDL options at the top. So this little thing with the range, TDL options. So if you want it to be physically realistic, what you should do is go look up the formula that Rick is going to give you tomorrow, plug in the parameters of your telescope, and work out what your noise per visibility is. But here, we just simply add it in units of Janskis. And now one interesting thing you can do is, add a couple of Janskis of noise per visibility to this simulation. Just as a good starting number. So we're going to pretend that we actually have a pretty noisy telescope with a warm receiver and whatnot. And then you have to compile again, and then possibly you have to, I recommend closing the bookmarks you had and opening output inspector again. So these are the new output visibilities, right, with noise added. And in fact, if you look at them, you know, this looks like, essentially it's nothing but noise, which is not surprising because if you remember, the brightest source in our sky model was 1.8 Jansky, and we've just added 2 Jansky of noise per visibility point. So our signal to noise ratio here is about 1, right? I mean, these things are very difficult to distinguish from actual noise, even though they're signal plus noise. So the interesting thing now is to make an image, and before you make an image, try to predict to yourself what you're going to see in the image. Are you going to see an image of noise and nothing else? But before you do that, I suggest go back to your text terminal, because you've got the FITS file sitting here, produced by the previous run of the imager. This one here. Now what you want to do is you want to rename that file, because the next time we run the imager, we're going to overwrite it. But what I'd like to do is to compare the two. So I suggest you take this file you had and rename it to something. For example, sim1.fits. Just to move it out of the way. Otherwise, you can always go back to the previous simulation and regenerate it. So once you've done that, go back to your simulation, which hopefully you will have run now. So you've got a bunch of squiggly lines full of noise, and make the image again. So did you expect this? Well, the proper astronomers would have expected, of course, but basically it looks identical to, you know, to the one we had before, right? Pretty much all the sources are in there. So despite the fact that we've got visibilities with a signal to noise of about 1, they still produce a perfectly good image, right? Now, to make sure this isn't an error or a bug or something, this is why I told you to move the previous image out of the way. What we can do is we can load the 2 images into Tigger side by side. So you can do this through the image menu up here. You go image, load the image, and load the old one. So now you're displaying 2 images. You can flip between them like this, or actually I prefer to use F6. That's a shortcut to blink. So if you just press F6, you're going to blink between the images. They might look different because you can see we're displaying them with different intensity metrics. So a useful thing to do is to click on the lock icon up here, hold it down, and say lock all to this. So you want to make sure that both of these locks are now in the lock position. And what that does in the FITS viewer, essentially it locks the 2 images to the same display scale. And now the 2 images are rendered in the same scale. If you blink between them, you are going to see a little bit of a difference, right? So if you blink, you'll notice the difference, right? The old image, well, as we would expect, there's a little bit of noise on top of the new image, right? The old image was a noise-free simulation. The new image has this little ripple, right? What we can actually do is we can get that ripple out and isolate it. And you can do this by, essentially what we want to see is the difference between the 2 images, right? A minus B. And that's very easy to do. You just go here to image, and you say compute image. And in this dialog, all you have to do is say A minus B. So one of the images is labeled A, the second one is labeled B. If you say A minus B, that will give you the difference image. And so that's the difference between the two images. Indeed, you can see that the difference is a bunch of noise, right? Now, the interesting thing is, why is the noise so low? If you want to measure the statistics of this image, there's two easy ways to do it. First of all, if you look at these numbers here, along the bottom, they're set to the minimum and the maximum of the pixel values in the image by default. So that always tells you the minimum maximum of the image. And the other thing you can do, if you right-click and drag a box over the image, this shows you some statistics of the pixels in the box. So if you do that, if you right-click and drag a box, then this display here shows you the min, the max value in the box, and crucially, it's going to show you the standard deviation. Which is like 0.01. So what's going on here? Can anyone explain this? We simulated visibilities with two Janskys of noise in them. And we made the image, and there's 0.01 Jansky of noise in the image. Any explanation for this totally magic, magnificent trick? I assure you the simulation is right. Yeah, Dave?
Isn't it supposed to do with the noises uncorrelated?
The noise, well, that's a good question. Actually, the noise is somewhat correlated. Because the noise is, your original noise is on the Fourier plane, right? So, on different scales, the noise is going to be correlated. But still, the level of the noise is, a factor of 200. 200 lower than the one we put in the visibility. So, how do you explain that? Where did the noise go?
But average the way.
Hmm?
But average the way.
Yes. So what?
The central pixel is just the sum of all the visibilities. So
Yes.
that,
Yes.
that
Exactly.
really get rid of the noise of that pixel and the same.
Yeah. Exactly. So when you do a Fourier transform to go from visibilities to pixels, essentially, if you write out what the Fourier transform is, every pixel is a sum of all the visibilities with a certain phase kernel. So essentially, your Fourier transform is averaging down the noise by a factor of however many visibilities you have in your observation, right? So in case of Cat7, that's actually not a lot, right? Because we only have what, 21 baselines. Right? 21 baselines times the number of time slots. But if you're thinking of something like the SKA, right, or even SKA phase 1, where you've got 156 antennas and what is it, 150,000 baselines, there's going to be a hell of a lot of averaging down in there. So in fact, it's this fact, it's this and only this which allows us to achieve all these record dynamic ranges and expect nano-Jansky sensitivity from the SKA. Because thermal noise in the visibilities is very high, but it gets massively averaged down when you do the imaging process. Okay, what I suggest now, has everyone managed to produce that picture, or does anyone need help? Somebody needs help?
How do you get the steps then? When I do like the zoom, like when I make a box, it just zooms in. Is it because I have a neck and I can't make it?
Coming back to my previous advice.
No, totally, I'm with you. So that's so sorry for me.
I have no idea.
There we go. Ha!
With the Fox, you can
Or
have
what you can do
There
when
we
you
go.
start
Steps.
doing that.
saving
They just recommended when I started working. It's good for other things. Good for something.
No space. Okay. And then that also. Okay, this thing is a keep sitting here. So then, how do you rename the file? Okay.
Kind of. I used to think
It's what I have no idea. Like how it's my enemy.
Well, the simulated data will stay in but in this case, for the exercise, I recommend just doing on because it only takes a second. So it's safer. Because you never know what else will go wrong. Well, it's possible to, what we can do is we can add images to the, so you can go to dialog that consists of point sources plus images, plus copy flows. I'm not going to show it today because it's advanced, but in principle for those kinds of things, it's images on this dial. So the other thing you can just not do something like that.
Yeah.
I see he's playing this thing down.
Yeah.
That's the story.
Quite a lot of stuff. It's the first time it was right?
So it's too bad.
Yeah, exactly. That's the thing, more or less. All the business my wife. Finally, I can understand.
It's that to no, I will do the first one first as well. And then you distract as well. Just distract.
It's very short connection, so you have to pass by the wireless. Same idiots. Where you on the
So now I just do
wireless.
So the other thing that people possibly understand is because you can actually sometimes leave and that's why you should do
call it the computer.
You see the signal.
Very no sense. Big yeah. So you see, it's beautiful. So you can see. So I like the figures. I've never written so much equation in really smart. So when I look at it, I virtually understand it.
This is fine.
So I took a look at it, it's not doing anything. Okay. Oh, no, this has an 8-hour battery. Okay. Okay, this is cold as ice. I think what that is that. Yeah, when that carrot lights and okay.
Sorry, this MV was so I tried the same thing. It's not MV, meeting small threads.
Oh my god, now what?
So now if you want to do it
Okay, but now it is that lost thing. Can you?
Okay.
Not yet the two next.
Not to make that way, it's
Oh, because it's 8 speed.